So everything works. So nice. The next talk has a very long title. I want to avoid to say it again, and therefore just Kazuki, you can start.
Yeah, so hi everyone. I'm Kazuki Ikemori from Tokyo Institute of Technology. So I will talk about the equivalence of expressive power between labeled effect calculus. So let me first start with some background. Effect handlers with first-class labels and control operator with first-class labels are used in several practical programming language for abstractions of computational effects. For example, Coca and TableLift have effect handler with first-class labels. And Haskell and Racket have a control operator with first-class labels. So labeled effect handlers and labeled control operator have similar functionality. This similarity has already been used to understand and implement the functionality of one from the other. For example, Serial et al. Has been used to implement labeled algebraic effects in OCaml using labeled control operators. So we concerned with the equivalence of expressive power between labeled effect calculus. To show the equivalence of expressive power between labeled effect calculus, between labeled effect handlers and labeled control operators, we aim to define translation that preserve type and meaning between the two types of calculi. If the equivalence of expressive power between labeled effect calculi can be shown, there are two benefits. The first one is that we can implement one labeled feature using the other. The second one is that we can apply the theoretical property of one labeled calculus to the other. In previous research, the equivalence of expressive power between effect handlers and control operators is shown by defining macro translations. Forster et al. Defined macro translations that preserve meanings only. Pirog et al. Defined macro translations that preserves both meaning and types. We can consider two approaches that are direct approach and incremental approach. In the next slide, we first explain direct approach. So one possible approach is to directly define macro translations of the calculi with first-class labels by extending the macro translations of previous research. However, a gap between the first-class labeled effect calculi and plain effective calculi. To bridge this gap, we need to address many issues. So we take incremental approach to define the macro translation between effect handlers with labels and control operators with labels. The first step is to define the calculus of effect handlers with second-class static labels and calculus of control operator with second-class static labels, respectively. In this step, we first show the effect safety of the control operator with second-class labels, which has not been shown in previous research. We then define these macro translations between the two and show that they preserve types and meanings. The second step is to define the calculus of effect handler with second-class generative labels and the calculus of control operators with second-class generative labels, respectively. In this step, we first address name escaping program using lexical scoping. This technique was used for algebraic effect handlers, but not for control operators. So we apply this technique to control operator and define a type system for control operators to prevent name escaping. We then define macro translations and show that they preserve types and meaning. The overview of our research is shown in this slide. So we formalized 4 calculi covering all combinations of effect handlers, control operators, and static generative labels. and show the equivalence of expressive power between them. Preparation for extension to the first-class levels can be done by this work. We explain the details of each step in the following slide, and we focus on static levels because generative levels is very similar to static one. So we first formalize the lambda FL that has effect handlers with static levels. These consist of labeled operations and labeled handlers. Operations are for performing computational effect, and the handler gives interpretations for these operations. Labels are used for associating an operation with a specific handler. This calculus is based on the earlier iteration on F programming language that has algebraic effect handler with labels, and we prove its type soundness. Yes, so let us look at the example of this calculus. First, the operation called do L is performed. L represents static labels. The program execution is then shifted to the inner handler with the corresponding label L. At this time, the program with the blue background is bound to the variable R as a continuation. Then by applying continuation R to 1, the program is resumed from the point where the operation was performed. Hence, the value 1 is bound to the variable state 1. Next, the operation called do L prime is performed. The program execution is then shifted to the outer handler with the corresponding label L. At this point, the program with a red background is bound to variable R as a continuation. Then by applying continuation R to 2, the program is resumed from the point where the operation was performed. Hence, the value 2 is bound to the variable state 2. Finally, the result of whole program is 3. The type system of effect handlers with static labels can guarantee that every operation is handled by a handler with a corresponding label using the effect system. The typing judgment of effect handlers with static labels states that expression E has type tau and the type variable environment delta, variable environment gamma, and label environment sigma. And the may perform effect rho. By determining whether rho is empty or not, it can be determined whether all operations are handled. So we prove that our calculus of effect handler with static labels meets effect safety. For example, we can statically judge that all operations in this expression are handled because the effects of this expression are empty. On the other hand, we can statically judge that this expression contains an operation that is not handled because the effects of this expression are not empty. Okay, let's go to the next slide. So we next formalize the lambda del L that has delimited control operator with static labels. Delimited control operators consist of two operators, shift 0 and dollar. Shift 0 operator is used for capturing a continuation, and the dollar operator is used for delimiting a continuation. Labels are for associating a shift with specific dollar. And we prove its type soundness. Let us look at the example of these calculus. First, we define a reader 1 and reader 2 functions that have shift 0 operator to get the value from a read-only state. The shift 0 operator of the body of the reader 1 function captures a continuation up to the inner dollar with a red label. It is evaluated to value 1. On the other hand, the shift 0 operator of the body of the reader 2 function captures a continuation up to the outer dollar operator with blue 1. It is evaluated to value 2. Finally, the result of whole program is 3. Yes, so in the next slide, we explain why is effect safety important for defining typed macro translation. A typed macro translation preserves effect safety. So the existence of the effect safety of source and target calculi is necessary to define typed macro translation. However, type systems of previous research for labeled control operators do not meet effect safety because these type systems do not have effect system. Hence, it is not possible to translate a labeled control operator in a type system of previous research to a labeled effect handler in a type system with effect safety. Since type system of previous research do not have effect safety, these type safety cannot ensure any shift operator is surrounded by data operator with a corresponding label. For example, this is effect unsafe program. This program is effect unsafe because this shift operator with label L is not surrounded by a data with label L. However, the type system in previous research cannot check for shift L operator that is not surrounded by data operator with the corresponding label L. To address this issue, we define an effect system of control operator with labels. So our type system can ensure effect safety for control operator with labels. We prove that our calculus of control operator with static labels meets effect safety. In this program, our type system can check that a shifter operator is surrounded by a data is not surrounded by a data operator with a corresponding label L. So in the next slide, we talk about type translation. We define the translations between Algebraic effect handler with static labels and delimited control operator with static labels. And we prove the type and meaning preservation property of them. Let me explain the translation from lambda del to lambda fl. The translation is represented as a ceiling bracket and extends Pirog's macro translation with static labels. The extended translation is not so hard, associating shift and data operation with static labels. A data operator with a label L is translated to a handler expression with the label L. This should intuitively make sense as a handler and a data operator play a similar role, namely to delimit the current continuation. The operation close past the continuation K to the operation's argument F. A shift operation with the label L is translated to a do operation with label L. The operation received a function that takes a continuation, which is translated to from the body of the shift operator. Yes, so let me explain the translation from lambda fl to lambda del L. This is opposite direction. The translation is represented as floor bracket and extends Pirog's macro translation with static labels. The extended translation is also not so hard, associating operations and handler expression with static labels. A handler expression with label L is translated to a shift operator with label L. This should intuitively make sense as a handler and a data operator play a similar role, namely to delimit the current continuation. The operation close of the handler is translated to a lambda term and applied to the data operator. A do operation with label L is translated to a shift operator with label L. This should also intuitively make sense as a do operation and a shift operator play a similar role, named to introduce an effect. The expression lambda x dot kxh in shift 0 operator represent the delimited continuation of the operation call, including the surrounding handler h. Okay, so we explained the Algebraic effect handlers with generative labels. So we format the lambda f L plus eta that has effect handler with generative labels. This calculus is extended by lambda f L that has effect handlers with static labels. Generative labels are generated at runtime. Lexical scoping prevents labels from escaping scope. By generating labels at runtime, users do not need to know the exact number of used labels. In the program example below, when reducing the right-hand expression is to the left-hand expression, a new static label L is generated. A new static label L is generated, and label eta is replaced with static label L. We next format the lambda del L plus eta that has control operator with generative labels. This calculus is extended by lambda del L that has control operator with static labels. Generative labels are generated at runtime. Lexical scoping prevents labels from escaping scoping. In the program example below, when reducing the above expression to the bottom expression, a new static label L is generated and generative label eta is replaced with static label L. So we define the translations between algebraic effect handler with generative labels and delimited control operator with generative labels. And we prove the type and meaning preservation property of them. Let me explain the translation from lambda del L plus eta to lambda f L plus eta. The translation is represented as cell bracket. The definition of the translation from lambda del L plus eta to lambda f L plus eta is almost the same as the translation for static labels. The only difference between translations of static labels and generative labels is that static labels are replaced with generative labels. The translation from lambda del L plus eta to lambda f L plus eta is represented as floor bracket. The definition of the translation is again almost the same as the translation for static labels. We just use generative labels instead of static ones. In this work, we can define 4 calculi covering all combinations of effect handler, control operators, and static generative labels, and define typed macro translations between the corresponding calculi. So our original research goal is to define translations between first-class labeled effectful calculi. The first-class label allow us to use labels in more flexible way. For example, we can implement ML-style mutable reference cell using first-class labels. As I said at the first slide, Coca has effect handlers with first-class labels and formalization of effect handler with first-class labels. Coca avoid name escaping using rank 2 polymorphism. So I would like to extend our calculi with first-class labels using this technique. To summarize, we formalize 4 calculi covering all combinations of effect handlers, control operators, and static generative labels, and show the equivalence of expressive power through defining typed macro translation between the corresponding calculi. Thank you for your attention.
So, are there any questions? So, please.
Hi, thanks for your talk. My question is, do you expect there is any specific obstacle for proving the translation with first-class labels?
Yes. So I expect extend the second-class type macro translation to first-class macro translation is not so hard because the Okay. So this work is almost completely prepared to the extent of second class translation to first class translation. So I think the most difficult part is apply to higher, so second rank polymorphism to the type macro translation. Yes, so I think.
So, are there further questions? Yes.
So for the to study delimited control, delimited operations, did you look at other formalisms, like for example the Laptopami-Matilda calculus? The one we had in our paper. That's based on classical logic, and you can express delimited continuations in there. It's a very elegant way to do that.
Yeah, if you have looked into other formalisms, like the paper they had.
So there's the Curien et Herbelin 2001 paper.
Yeah.
So that's a calculus in which you can express delimited continuations directly.
Okay, I see.
So there is another calculus
Yeah.
where they can express the limited continuations. Whether you have looked into those papers or whether you know those papers. If not, it will be a good, a very good suggestion.
Yeah, so I haven't not looked at this paper. So
Yeah. So because I see that you use a CPS translation. So you can avoid that if you go to that kind of calculus.
Yeah. Yes, yes. Thank you so much. So I'm going to look this paper. Thank you.
Okay, so I have also a question. So you showed this interesting equivalences, and some part of this conference is also related to the practice of declarative programming. So are there also practical consequences of this work? So
Practical. So sorry.
how you can use it? So these results are there?
So you mean so my work can be applied to the practical programming.
Yeah.
So yes. So this is my long-term goal. So I would like to make a programming language using these macro translations. Yes. So I think the difficult part is in current formalization is subtyping over the effect typing. So it is very problematic. This is a problematic situation. So the typing inference. And so how to address this issue is my current issue.
Okay.
May I add one thing? So one of the point is one of his point is to use macro translation. So almost syntactically you can convert a program from one formalization to the other. So one of the idea is that, for example, in OCaml there's a delimited continuations, but no effect translation, no effect system. So the effect systems maybe we can introduce the effect systems in OCaml just by macro translating to realize that.
That would be interesting, yeah. Okay, then thank you very much again.